Hey everybody. I was going to say good morning, but I don't know when you're going to watch this. So I'll just say hello. Hopefully you're having a good break from classes for the week. Um, what I plan on doing with this video is just going through a few of the questions from the assignment that is due when we get back. Apologize for the delay. I was hoping to get this done on Sunday, but a lot of other stuff happened. I remembered that I had to get a CIS test ready for my class. My first hour class actually had to take their test on Monday, and so, well, enough of excuses. Let's get to look at this worksheet.
All right, well, I won't go through the entire thing, but I'll maybe choose a couple representative questions and just talk through those. I've got a few of you who asked for mostly on the second half of this, so we'll make sure we get there. But on the first part of this, the day 12 independent and dependent events, maybe just a couple select ones. I'm looking at this section. Number 3, coin lands heads up on every toss when it is tossed 3 times. These are independent events. Each one resets. Every time you flip a coin, you have a 1 out of 2 probability. So the probability of having heads, then heads, then heads is a half times a half times a half. Each one of those independently is 1/2. So 1 out of every 8 times, you'll end up with 3 in a row heads. But then number 4, rolling an even number and then rolling a 6. Well, I take it back. Those are independent also. I roll a die, a regular 6-sided die, I guess I'm assuming. Yep, they're calling it a number cube, so I guess it would have 6 sides. So rolling an even number, the probability of that is 1 out of 2. And then the probability of rolling a 6 is 1 out of 6. 3 of the 6 possibilities are even. 1 of the 6 possibilities is a 6. And 1/2 times 1/6 is 1/12. Then we could convert that over into decimal form. I'm not sure what that is, like 0.08 or something like that. But I'm okay with the fraction form of those answers. Let's find some dependent examples. And actually, that next one's a pretty good one. Because with the first one, we've got 20 checkers, 10 red, 10 black. And we're reaching in. Part A says we draw a couple of them out with replacement. That means we take one out, we put it back, and then we take another one out. And so we may end up getting that same one back. And so for this, it's basically the same. These are independent events. So I draw one. Let's see. Of the 20 checkers, 10 of them are black. So it's 10 out of 20 or 1/2. And then we put that one back in. We got exactly the same situation. We still have a 1 out of 2 or a 10 out of 20 probability of drawing a black one. So a half times a half is a fourth. Then we can certainly call that 25% or 0.25. Any one of those is okay. But then part B, now we've got dependent. Selecting 2 black checkers when they're chosen at random without replacement. So I take one out. The first checker I pull out of there, yeah, there's a 10 out of 20 probability that that one will be black. But now, since I've drawn a black checker from the bag, that means there are both fewer black checkers and fewer checkers altogether. Now I had 10, now I've got 9. I had 20, now I've got 19. And so of the 19 checkers left in the bag, 9 of them are black. And so we end up with 9 out of 2 times 19 is 38. And I'll just get an idea. This would be slightly less likely than drawing 2 black checkers, but not by much. Let's see what it is. Oh, you can't see what I'm plugging in, but I'm just doing 9 divided by 38 on my calculator. And yeah, just slightly less than 25%, about 23 we'll call that 23.7%. Again, slightly less because that second draw has a little bit lower probability. Let's see. Trying to find another good one to illustrate dependence. Let's see. Thinking maybe number 8 would be a good one for us to look at here. A couple number cubes are rolled. One is blue and one is yellow. Explain why they're dependent, and then more importantly, let's find the probability. So a yellow cube is greater than 5, and the product is greater than 24. And these are dependent events because if my yellow cube is greater than 5, then it's going to be more likely that my product is going to be bigger than 24. So I'm just going to think of the 36 possibilities I have when I roll two different number cubes or dice. Yellow cube being greater than 5, well, that's a 6. So the only possibilities would be 6 rolled with a, let's see, if I'm rolling a product of 24, 6 and 4 would not be greater than 24. That would be 24. So I guess a 6 rolled with a 5 or a 6 rolled with a 6. Those are the only possibilities where my yellow cube is first. So my yellow, what's the other color? Blue. So yellow 6 and blue 5, yellow 6 and blue 6. Those are the only two possibilities of those 36. And so my probability is 1/18 of having both of these things happen, both a yellow cube greater than 5 and a product greater than 24. This would be 1/6, and this would be, well, let's see, guess it would be 3/36 because I would have 6 and 5, 6 and 6, or 5 and 6. And the answer I'm getting is not the product of those two. I'm treating those differently. And then finally, part B, a blue cube is less than 3 and the product is 8. Oh, let's see. I'm just going to think about my possibilities again. So now my blue cube less than 3. So it's either a 2 or a 1. So if I've got a blue 2 and my product is 8, well, then the only thing I could have would be a yellow 4. If my blue cube is 1, then my yellow cube, well, I guess I can't do that because there is no 8 cube. So I think that's my only possibility. Blue cube is less than 3, so 2 would have to go with the 4. A 1 would have to go with an 8, but there isn't an 8. So it looks like the probability of this happening, there's only 1 out of those 36 members of the sample set for rolling 2 dice for which that works. Okay. Now, the questions that I was getting mostly were from the conditional probability, and so I'll definitely want to spend a little bit more time on that. And as I look at the questions here, the thing that jumps out at me, and maybe this is why people had so many questions about this, is that we're going to have to do what we did with these tables previously, and it's going to be important for us to add up these columns. When I say find the probability that a shipped bulb is not defective, well, the shipped bulbs, that's all of these. This 10 plus 942, I want to consider all of those at once. So when I add these up, it's important that I look at that total. And I say that the probability that a shipped bulb is not defective, by the way, another way of saying this is the probability of not defective. And then I use this kind of vertical line to show given that it is shipped. And make sure that I'm reading this right. Probability that a shipped bulb is not defective. So what is the probability that it's not defective given that it is shipped? Well, the defective ones, there's only 10 of them out of those 952. And I'll contrast that with the second one. What is the probability that a bulb is defective and it is shipped? Well, now I'm looking at just these. It's these 10, but it's now out of the total. Out of all the bulbs, what is the probability that it's both defective and shipped? And so what I'm looking for here is the probability that the bulb is not, or wait, that was not defective. This one is defective. Shoot. So this is defective and shipped. I think I did the first one wrong. Not defective, given that it is shipped. Take that back. Not defective was 942 out of 952. And then here I'm looking at the probability that a bulb is defective and shipped, and that's 10 out of the total, and I haven't found that yet. 45 and 3 is 48, and then 952 and 48 is 1,000. I would recommend when you do these that you double check and make sure that the other column works. 10 and 45 is 55. 942 and 3 is 945. So those two add up to 1,000. Those two add up to 1,000. That's a good way to double check. So it looks like I've got 10 out of 1,000 bulbs, which would be the same as 1 out of 100. That would be either 0.01 or 1%. Any one of those is okay. Although I guess I should say I would reduce a fraction to 1/100th. So that's the idea there. I'm going to skip ahead. Questions 8 and 9 were asked specifically for, so we can take a look at those. But I'm actually going to start by doing the same thing that I did already on the previous one, and that is add up these columns. If I'm looking at Roger Federer's service points, which, by the way, my brother was living in Switzerland when Roger Federer was at his prime, and he was like a god over there. He was just the biggest thing in sports in Switzerland. Sorry, this is 98 total times that he won, and let's see, 53, 56 times that he lost his service point, and then 3 of those were by, let's see, I'm running out of space here. Can you see that? Double fault. I've got 56. We got the second serve in, and then 60, 95. Hopefully I'm adding these right up in my head. But I suppose I can take my own advice and double check and make sure. 98 and 56 is 154. Hopefully that works out here. 95 and 3 would be 98. 98. Well, there's 98 and 56 again, so 154. So looks good. So now answering these questions. What's the probability that Federer won the point when his second serve was in? So I'm only considering the second serve. I could say this is the probability that he won given second serve was in. So I'm only considering the second serve in. Out of those 56 times, he won 34 of those. And then I'll reduce that to 17 out of 28. And if you want to convert to a fraction, you can, but I will leave it like that. When Federer lost a point, what is the probability that he double faulted? So now I'm looking at this column of the times that he lost. This is going to be, what is the probability that he had a double fault given that he lost? When he lost a point, what's the probability he double faulted? So in this category, in the times that he lost, how many of those did he double fault? And that's 3. 3 out of those 56. And that one's not going to reduce. So that's the idea on those. I'm just going to skip back here and say that it's very important on problems like 3, 4, and 5 that you've got these things written out. I took the time ahead of time and I just added up all of the rows. I added up all of the columns. And then I double checked to make sure that the sum of the totals was the same for both the rows and the columns. We're talking about 65,846 people total here. And so if I'm answering these questions, doing this work should make these problems a lot easier. Let's find out. Probability that a selected person is from Cuba, given, I'm going to write this out in math notation, probability of Cuba given that they immigrated in 1990. So I'm only looking at the 1990 category. Of the ones who immigrated in 1990, how many of those were from Cuba? Looks like 10,645 out of the 16,997 total. Whoops, 16,997. A little bit sloppy on that one. Probability that a person came from Spain and immigrated in 2000. This is a little bit different. This is probability of Spain and immigrated in 2000. So here again, we're looking at just the intersection of those two. So Spain and 2000, we're looking at 1,264 out of the total. I'm not just considering one category or the other. I'm considering them both at the same time. 1264 out of the total 65,846. And 5 is pretty similar to number 3. I'm just going to skip ahead. Let's see. This is the same idea. The difference on this one is that you'll be doing a little bit of an estimate. Whoops, sorry about that. So is that 21, 22, 23? That used a little bit of an eyeball, and if your answer disagrees slightly with my answer key, then I wouldn't worry too much about that. Let's maybe just take a look at one of these. Probability that a Spanish club member is a girl. I'm going to consider this to be the probability. Let's see, that a Spanish club member is a girl. So what is the probability of a girl given that they are in Spanish club? And so let's see, Spanish club members. Well, it looks like I'm considering all of them. So I'm considering everybody. Didn't say anything about 1 year or the other. So it looks like I'm thinking about everybody. So I'm going to have to estimate these. I hate to do this because now you're all going to copy down my estimates. That looks to me like it's about 25. It's a little bit less. We'll go with 24. Let's see, this one's a little more than 50, maybe 51, 52. I'm going to go 52. I guess I'll have to go about 53 on that one. And then here, the seniors, we've got just a little bit more than 70. I'll go with 71 for that one. And then this looks like a little less than 50. We'll go with 49 for that one. And again, if you're looking at this and your estimate is a little bit different than mine, then I don't think we're disagreeing. I think we're just misinterpreting or having a difference. Mine is no more right than yours will probably be. Anyway, probability that I have a girl looks like the red is girls and the blue are boys. How stereotypical of them to do that, but that's fine. The girls looks like got 25 and 52. That's 77. And then 71 more, so 148. So 148 out of the total. In my total, I've got 148 girls. And I've got, let's see, 24 and 53 is 77. 77 and 49. Oh boy, I'm testing myself here. 77 and 49 must be 126. Which brings us to a total of, boy, I hope I'm doing this right. I have a feeling someone's going to send me an email and say, Mr. Crow, when you found the total number of students, I'm just going to go ahead and double check and save myself the time of correcting this later on. So my girls, 25 plus 52 plus 71, that was 148. And then when I add the boys, 24 and 53 and 49, 274. Well, look at that. I guess I got it right. So that's what we're doing. That's what we're doing there. And then finally, the last problem. I think I'll leave it to you to look at B and C, but how are we supposed to fill in a table that has blanks in it? Well, this seems to me like it's a little bit of a Sudoku puzzle. Sudoku. Different people pronounce it differently. But as I look at this, I'm going to look at gaps that I can fill in. For example, in this first column, I'm only missing one thing. I know that these three have to add up to this. So I can take 3761, take away 61, take away 598. So that last one, that top one, must be 3102. And that all of a sudden makes the top row over here possible. I couldn't do this before, but now I know that these three have to add up to that total. So 3102 plus 3197 plus 3237. So this total needs to be 9,536. And you probably kind of get the idea at this point, but frankly, I'm having fun, so I'm going to keep going. Now in this row, I've only got one thing missing. So I know that these three add up to 2321. I can take that 2321, subtract the 598, subtract the 877, and get the 846. And now this row, or sorry, this column I can do. These three have to add up to that one. And maybe I'll stop at this point and let you guys take over for the fun. I will post the answer key for this. You'll be able to check and make sure that yours are right. But that's the idea. As you're filling it in, more and more rows, you'll be able to figure out, I can't do this row yet because I've got two different things that I'm missing. But if I figure out this column, okay, so these three add up to that. I'll be able to find that one, and then I can do that row. And then once I do that row, I can do this column, and you'll be able to fill in everything. But I think I'm going to stop at this point and say, hopefully this helps out for those of you who had questions about this assignment. If not, send me an email. It is only Tuesday for me. So if you work on this and have troubles, I should be able to respond to you later in the week or the weekend. So there we go. Have a great day. See you guys later. Bye-bye.